Okay, let's start. May I ask to please turn on your camera? Thanks now. Others, please. So today we are going to discuss some of this pipelining issue and a little bit of performance analysis. We basically can see that we cover a good part of pipelining, and since it is related to previous type of microarchitecture, single cycle and multi-cycle, this is again pipelining, as you know, improved performance, but we have not discussed formally how this would affect performance and the kind of variations that we saw with respect to, for example, the issues that we will face in pipelining and how these decisions that might be a easy or sophisticated solution for resolving pipelining issue, how these might affect performance down the line in the pipeline architecture. Before we go into detail, do you have any question for me? I sent out an update over Piazza. Hopefully you received that about this new homework, the last homework, and the final. Hopefully you're clear about it. So this, basically all assignments that you have seen so far should pretty much cover all material that you will have for the final. So you have some examples, and again, reviewing the textbook slides and previous lectures is definitely useful. So you have all materials, and let me know if you have any concern, if you have any question, if you want any help, and so on. Specifically about pipelining, the textbook, specifically section 7.5, and with respect to these specific issues that we'll cover, 7.8 is these sections that I highly encourage you to review. These are very useful and easy explanation of pipelining and also the issues that we have reviewed and we are going to review today, and give you a better idea. So if you put them alongside what we have been discussing about pipelining, it gives you very clear vision about the concept that you might be still vague about this. So I'm sure these sections would be very helpful. Highly encouraged. So we discussed about these fundamental ways of handling dependencies, if you remember, so I'm not going to discuss them again. Hopefully you're clear about it. We finished off with this example. This is again very easy program that has 4 instructions: load word, and, or, and subtraction, and there are dependency between the three consecutive instruction that you see, and or and sub with respect to load word. So load word put the content into the value that are located at this memory location into S0, and all other three instructions are dependent somehow using this value that will be stored in S0 for doing ALU operation. And all of these three instructions, basically these are ALU operation that require the content of S0, in addition to some other registers, S1, S4, and S5, which has no dependency to the load word instructions. But S0 create this dependency. And specifically, we discussed like within this pipeline, the last instruction, subtraction, is not necessarily a dependency because of this assumption. Given this assumption that we first write into a register file and then read from it, so the last instruction sub, there is no need for resolving this dependency. The value of the register S0 will be in place once the last instruction needed this value, given that this last instruction has started in cycle 5, right? But and or second and third instruction needs to be stalled because of this dependency that we just talked about. And as you know, for and if you think about this, why this has happened, how we can make a sense out of it. I mean, we saw this dependency in a slightly different program, but specifically with respect to this program, you see load word in the first instruction. And load word is a specific instruction if you think about it, because the execution, the actual execution is happening in 2 cycles for this instruction, as opposed to other R-type instruction. Let me make it clear for you. In R-type instruction, where we require to do an ALU operation, we need 1 cycle to do this ALU operation. This is, for example, for AND. In this cycle, for OR in this cycle, basically the rest, their other stages are either like fetching, or like, for example, in this memory access, doesn't need to do anything. So this and or stop doesn't do anything in this memory access stage. The most important stage, which requires 1 cycle, is this ALU operation. But in load word, if you think about it, we need 2. We need both ALU for calculating the actual address of the memory where we need to get access to, read from. So we need to do some ALU operation, because this is a base and this is the offset. So we need to do some calculation to calculate the actual memory address. In this one cycle, we only calculated the memory address. Not useful. Nothing is ready. Nothing can be forwarded because nothing actually got executed in this, even though like we have this in the execution stage. But after this execution stage, whatever we calculated actually is not useful for forwarding to others instruction, because load word is a specific, is with respect to comparing with the ALU R-type instruction, require to read from the memory in order to produce something useful. So the actual execution, the actual value that is going to be useful is calculated in two stages. I require two cycles in order to produce this value. So again, this is important to compare. If load word would have been, instead of load word in the first instruction, we have had an R-type instruction, then we were in a much better position. Why? You know that if, for example, if load word were something like AND operation, right? And then, or add I operation, whatever R-type operation, to produce a value to put into S0, then we have had the value, the useful value, right after we have done the ALU operation. And then this can be forwarded to the consecutive operation instruction, and then there wouldn't be any need for stalling these instructions as a result, which is good. So this is a good example if you think the ordering of instructions, the type of instruction that create this dependency also matters because of this semantic that each instruction have, or each type of instruction might have. So this, make sure you understand this differences, and because this helps you to understand the solution for resolving this pipeline issue better. So many of these really depends on the type of instruction and why some of these software based resolution that can be taken care of at the compiler level sometimes is more efficient. So in terms of the solution at the hardware level, we have discussed, and we had an example that stalls can be supported by adding some input to the fetch and decode pipeline, register some additional hardware and control signal, also control signal for resetting or clearing the execution pipeline register, and all of this is the software, sorry, at the hardware level that can be handled. But you remember we needed new component at the macro architecture in order to take care of this, in order to enable setting, resetting, some of these control signal. For example, for load word, specifically, since we need to make sure that the following, in this example, the following two instructions are basically needs to be stalled, we need to have mechanism to enable that at the hardware level. And stalling, for example, in this case, you need to at the decode and fetch a stage, you need to send a specific control signal, in this case, stall D and stall F, stalling stage decode and fetch accordingly in order to force, basically you can think about this as some mechanism to stop these following instruction. In this example, these two instruction in order to stay there and not move forward to the next stage when the first the load word instruction is moving, right? So this is what we have discussed, if you remember, meaning that the first instruction in this example, load word, will move, but we want to have mechanism in order to stop or stall the following two instruction as a result. And flush E is also asserted to clear the content of execute stage of the pipeline register. Basically, you can think about it as like hardware level bubble. Basically, clear. You make the content of the pipeline invalid. In this sense, you created artificial bubble in the pipeline. Remember, we have this hazard unit. You see here stall F, stall D. These are like new control signal that you need to send to these latches to make sure that these instructions are kept there. And we need to flush, to send flush D in the execution stage in order to handle this stalling for the machine. And we have discussed these control signal, forward A, forward B, in order to like for the case where we have we need to forward some values to the next stage. In those cases, these are some of the data pipeline additional data paths that we added to the macro architecture in order to enable this value forwarding, etc. So these are like this is the updated macro architecture with all of these additional stuff that was related only to pipeline. So like we didn't have these elements, these components in multi-cycle. So these are like additional data paths and control signal that we have added to the macro architecture in order to enable pipelining and also resolve some of these issues that we discussed in the pipelining by value forwarding to the next stage, by stalling this necessary instruction where it cannot be really resolved by value forwarding. If again, like if we could have the value, we could simply use these control signal and additional data paths that we added to the macro architecture to forward the value. But in particularly this kind of scenario where, again, this scenario exists, right? It's not the case that we always have the beauty of basically, we do not have the case that value forwarding can resolve all of these pipeline issues. And this is one of those examples where really value forwarding cannot help because of these load word that require 2 cycles to calculate something useful. And when the value basically has produced, we needed this value here, but again, could be forwarded after one stage of stalling has happened. Is there any question here? Hopefully this is clear, right? So again, you need to put together, so far we have added like 2 chunks of changes to this multi-cycle microarchitecture. Sorry, 3. One was this increase in these latches, right? So this control signal needs to be forwarded, right? Needs to be kept in order to enable this pipelining. We have discussed this in the first place. That was important extension. And then we have discussed once we have this pipeline, it's not the case that the pipeline will move forward beautifully until the program finished. There would be a need for handling dependency. Basically, this is not the case that we do not have any dependency. That's ideal, but this is not the case. In order to handle this dependency, value forwarding might help. We discuss how we do that at the hardware level. Again, value forwarding cannot handle all scenario. We need to stall, and these are the new pipeline or microarchitecture additions that needs to be added to the microarchitecture to handle this. In addition to data dependency that we discussed, right? So again, like previous example, make sure you understand this, like previous example was also a data dependency because data will produce that needs to be used in other instruction in order to calculate or execute other instructions. There is also dependency of control type. It's called control dependency, which is dependent, some instructions are dependent on the value of PC. Basically, what would be the next instruction that needs to enter to the pipeline? It's not the case that always next instruction should enter. Why? Because we have some jump instruction, right? So we have some special instruction that you're aware of that change the sequence of the program, right? If we have a jump, then next instruction is not located at PC +4, might be somewhere else in the memory, which is determined by these type of instruction like BQ or jump and so on. So So we need to handle data dependencies as well, which is going to be important and affect performance to a great extent. And let's discuss this. So in terms of BQ, if you think about it, branch is not determined until fourth state of the pipeline, and in the fourth state, basically, so BQ we need to first fetch it, and then we have this decoding. After decoding, we need to do LU operation, check the equivalency of the value of two registers, and then we can generate this if these are equal, then we can generate this the next PC, which with a specific address. So if you remember, this contour signal PC source is calculated at stage 4 of this instruction. So branch is not really determined until the fourth stage of the pipeline. And instruction after the branch are fetched before the branch is resolved. And if you think about it, it's too late, right? So if in normal condition, and this is one example that you can think about it. So in this case, we have a particular program. We have BQ instruction here. Essentially, we compare T1 and T2, and we have immediate at the end, right? And then we have some instruction afterward, these and or subtraction ALU type of operations, R type operations. So when AND comes, this value we don't know. So at this cycle, we don't know whether we are going to jump in another location or not, right? Because again, this decision will be revealed, basically will be calculated at the stage 4 of this instruction here. So this one needs to be entered given the assumption of sequential execution. Okay, given the assumption that we execute, we enter the instruction to the pipeline if we don't know whether we are going to jump or not. Basically, this is a scenario where we want to, by default, move to the next instruction, or basically you can think about it as a strategy. This strategy could be differently, and like we will discuss it briefly, not in much detail because it is an advanced topic. This is somehow very much related to machine learning and prediction. We don't have enough time to cover it. It's a very interesting topic, actually, branch prediction. We are not going to discuss it, but in advanced computer architecture course will be discussed extensively because simply so many approaches out there. and so many interesting approaches out there can be discussed. So basically, in this strategy, we assume that like we by default move to PC plus 4, and if it turns out to be a branch taken, then we need to get rid of this instruction that has entered to the pipeline. And in this scenario, if you think about it, since this value, this decision will be determined in stage 4, all of these these 3 consecutive instruction has to be entered into the pipeline. Simply even like the last one, the fetch part will happen at stage 4. We still don't know because we can basically read from this memory in the second half of the cycle. So the value become known at cycle 5, where 3 unnecessary instruction has entered into the pipeline, assuming that this branch will be taken, assuming, right? Let me reword it so you understand fully. In this case, like BQ, again, one of these exceptional control instruction, right? Depending on the value of register, in this case T1, T2, a branch may be taken or may not, right? In this particular example, as we discussed, if branch taken, we basically 3 instruction has entered. If branch, let me make it formal. Assuming that we execute this a strategy that we just discussed, basically the next instructions will enter to the pipeline. If we don't know if we don't have if we don't know basically whether the branch is taken or not, basically if we don't know the value of BQ comparing of T1 and T2 in this case, or we don't know yet the next PC value, right? This SR says that the next instruction should enter to the pipeline, right? Assuming these 2 assumption that we have, then in this case, these 3 instruction will enter and needs to be flushed out because they should not have been executed in this scenario. Okay, but if it turns out to be that the branch should not be taken in this execution, then it's good. So basically, we don't need to pay any penalty in this scenario. So again, this is somehow you can think about it as a kind of a stochastic execution, right? Depending on the program, depending on the previous value that reside in these 2 registers in some execution, right? And depending on the program, again, like, and assuming that we follow this strategy, sometimes, actually most of the time, we need to pay the penalty, and sometimes we are good. We don't need to pay any penalty. But penalty, I mean, flushing the instruction that we did some part of the work. And if you think, For the AND, we need to flush it after 3 cycle has already been executed. For the OR, 2 cycle. For the sub, 1 cycle or 1 stage has been executed. And these are the work that the hardware, the architecture, the machine has executed, but should not have. So basically it was wasted execution. You can think about it that way. And we need to flush them out, get rid of them. But sometimes we do some work and it will turn out that these works were necessary. Okay. So this is about this particular control dependency at the abstract level in the context of this particular program. And make sure you understand this very well. There will be some question about it, most probably in your final, because it is important. And again, we have this a strategy of always not taking prediction. And you see prediction here, right? Again, you may ask, okay, this is one strategy, right? Let me repeat that again. This is one out of many existing strategies. Actually, this strategy always not taken in reality is not the best. Actually, is one of the worst strategy, because in real program, based on empirical evidence that we have of executing programs, most of the time branches are taken. So most of the time, not all of the time, most of the time. This is based on empirical evidence of real programs, not synthetic programs, right? And the intuition is that most realistic programs, and this comes from like not one program, 2 program, numerous type of benchmark program that researchers have looked at. Some construct are used very often, and one of these constructs is loop. And in the loop, you have this if part, right, where you determine, like you remember how you programmed a loop in assembly, right? So use one of these, control instruction like BQ to determine whether you want to execute this, basically the loop logic inside the loop or instruction inside the loop, or you want to like basically exit this this loop. Okay. And these constructs basically exist in all programs, which is why basically a strategy like always not taken is basically is not necessarily the best, or is the one of the worst based on empirical data. Okay, hopefully you understand this, because let me make it more clear for you. So you remember, like in assembly, right? So you have had some instruction, right? Some instruction, and then at the end you had some instruction like EQ, which basically like this compare the value of like some registers, right? And then you jump to like some other part of the memory, right? Or this could be also like you could also have like some control inside. Like I'm just giving you some random program, not necessarily following a specific translation of a C program to assembly, but you have seen in the example that you wrote so far of this type of assembly or this type of program structures, right? In this case, like if we have a loop that imagine that this will execute 1,000 times, right? This means that this branch is taken 1,000 time and not taken only one, right? Once. And we have loop construct in most program, actually several loop construct in realistic program. And as in like program like machine learning, we have so many loop. In other scientific programs also we have like so many loops because we do some calculation. Even in business systems also we have loop because we do some calculation. And if a loop is executing 1,000 times, the branch is taken 1,000 times, only one time is not taken when we want to exit, right? If it's like executing million times, is even worse, right? And that's why this strategy is not actually a good strategy overall. But the good news is that we have sophisticated type of branch prediction. People have been working on branch prediction ideas for many years now, and now microprocessors have very sophisticated branch prediction embedded in them and are used, which has a massive influence on performance of the system. Is this clear for you? Hopefully this makes sense. Okay, good. Again, to emphasize, branch prediction is important, always not taken, is not the only strategy that we have here. And the cost that we pay is the number of instruction that we need to flush. And like one proxy or the penalty for this is the number of instruction that needs to flushed when branch is taken. this is a proxy for the misprediction that we have. But this penalty can be reduced depending on the program by determining the branch earlier, determining whether we should actually branch or not, whether basically we do not need necessarily to wait until the fourth stage of the pipeline in order to know the result, in order to reveal the results. Because essentially, if you think about it, the value of registers, you know the value of registers in the decoding stage. Since you know the value of registers in the decoding stage, you can again do something about it. You can maybe add some logic to instead of waiting for the next stage ALU to do this comparison for us, maybe you can like pay cost, add a piece of hardware, a component that do the comparison for us in the decoding stage, right? Since we know the value of these two registers in the decoding, maybe by adding some cost to have a hardware there for comparison, you may be able to do better, right? To be more specific, and this is the original pipeline that we basically the pipeline that we already have, right? So in this case, since we in the this is the decoding stage, right? Since we already know in the decoding stage, right? In the second part of the cycle, actually, we know the value of these registers. Maybe we could add additional components to check the equality of these two values and generate this PC source D right in this second stage instead of waiting for the ALU in the next stage and like doing this comparison in doing this and in the fourth stage. You remember, like here, you remember we had this and here. So what we did this comparison with ALU, right? This ALU would generate this 0M, and then we simply had branch E. Here we forwarded it. We didn't use this branch E in this stage because simply we didn't know the value, okay? So this is, and also we had actually like branch D in the decoding stage. The first stage that we know this branch D signal is in the decoding stage, right? Because right after we decode, we know what instruction it is, right? So we know this signal in stage 2, but you see that we simply forwarded that to the next and next. So we forwarded to 2 stages without using it, and we did this and in the 4th stage because we needed to wait the 3rd stage to compare these 2 values through ALU. And then once we calculated this, we we had this AND in order to calculate PC source M. But it was not really necessary to do all of this forwarding. Maybe we could, like, again, maybe we could add this additional hardware to check the quality and then do the AND right in this stage. And then we have this PC value that we need to jump into in the second stage instead of fourth stage. So we expedited this calculation into two stages, right? We basically have this decision. We know this decision whether the branch is taken or not in the decoding stage. Does it make sense? So as a result, since this is the case, since we have we know whether we need to branch or not in the second stage here, then we don't really need to pay the penalty of moving these 3 instructions to the pipeline. Only one instruction has to enter to the pipeline, because we know this decision at the end of the cycle, but at the beginning of second cycle, we need to basically add this instruction to the pipeline anyway, right? Because we don't know the value of this decision at the beginning of the second cycle. We know it at the end of this cycle, right? As a result, we need to pay one penalty instead of 3 penalty, right? So we save 2 instructions in this case from flushing these instruction, unnecessary execution of these 2 instructions, or and sub in particular. But again, the reasoning that we just had this instruction, this and has to be executed. Okay, hopefully you understand like why this is moving to this at this memory, right? You remember the semantic of BQ, right? BQ was the piece increment 24. We have 40. If you add them up, is 64, right? If this is taken. Do you have any question? Okay. This is again one of these new idea of LE resolving, this pipelining issue and the cost that we need to pay. And this is with respect to this control dependency, right? Again, like we had data dependency. Now we have this new type of dependency, control dependency. And we have one solution for that, early branch resolution. But again, there are some advantages and disadvantages with respect to this solution. The advantage is that we reduce the branch misprediction penalty. This is good, which result into reduced CPI, right? Control cycle per instruction, essentially, right? Or average CPI. But there are some disadvantages as a result. This may increase the clock cycle time. Can anyone say an intuition why this may increase the clock cycle time?
You end up having more hardware that you have to use.
No, you're muted.
Oh, I think I unmuted myself. Am I good now?
I cannot hear you yet.
I can hear him.
Okay.
I hear him.
That's weird.
Maybe it's, sorry, maybe it is, let me check. Maybe it's my, can you say again, Noah?
Yeah.
Still I don't have why. Oh, okay. Let me change the setting. I think now I have it. Can you repeat? Sorry.
Okay, you can hear me now?
Yes, I can hear you now.
Okay. So one of the things that I thought about right away when you asked why is now that you're adding more hardware to the circuit or to the architecture, you're going to end up having more of that delay go through in your critical cycle time. So if we have a very long set of processes in our microarchitecture, a very long set of instructions, we're going to end up having a longer cycle time per each individual in a single cycle. But if you branch it into multi-cycle, it's going to take the longest of those stages, or the pipeline is going to take the longest that the stage would take.
Perfectly explained it very well. I don't need to add anything here, right? No, I explained it very well, right? So basically, there is a chance to increase the critical path due to adding this new hardware. And obviously, like in addition to this increasing clock cycle, maybe as a result, it doesn't mean that it's necessary increase the clock cycle time potentially, but also we need to add right hardware, so it means that more cost. And also this new hardware that we add, this little thing that we separated from ALU and we added in this stage is not going to be used by other instructions. So basically this was the cost that we paid for like one type of instruction. Others will not use it, which is like waste. Okay. And also like you need to add these muxes, etc., in order to have a in order to like have this data forwarding and also branch prediction, where you need to forward some value from like later stages. Right, especially imagine that the value of an instruction, the value of a register is going to be produced. Like imagine that we have a program for the previous example that produced the value of T0 and T1 or either of them in previous instructions that has not yet gone through the write back stage, right? So this means that for this example, here we need to have T1 and T2, and in this example we assume that the correct value of T1 and T2 are there, at this cycle are already written to the register file, and these values are valid and has no dependency, or if they have had dependency, they are already resolved, and these values are valid and can be used right away. But this is not always the case. You could have some instruction prior to BQ that has not yet executed or gone through the write back stage. So, so simply, we do not necessarily can assume that T1 and T2 contain a valid value when we are ready to read them for BQ, right? And in this case, again, like we know that how to resolve this, we can do data forwarding from whatever stages they have in, say, like write back directly into this logic, right? So in this case, like we simply forward this to we put a mux, right? We forward this. You see this data pipeline, right? So if you follow this data pipeline, you see from here the memory access, right? So here, like we say, we produce the value that we want to write, and then we simply use that as an input to this muxes. So this can be forwarded whenever we have this situation, right? So we can do data forwarding for ellipse branch resolution if the value of these registers are not valid from the register file. Hopefully this is also clear for you. Okay. Again, there are some smarter way of doing branch prediction. You can guess. And you can, one very simple intuition that you can have based on this intuition, you can build such branch prediction method is simply to use some historical execution of the program, right? So once you have a historical execution of the program, then you can build a statistical model to do prediction for you. And this is like a one-on-one machine learning problem, right? So you have some historical execution, meaning that you have like many execution of the program, and you can see that like in 98% of the execution, given this context, based on which the program is executed, because each program is executed in a context, right? You can see that the branches has been taken and in 2% not taken, right? So based on which you can build a model and use that model to do a good prediction, right? And good prediction reduces the fraction of branches requiring a flush, right? So these are some like, and even like this, with this simple scenario, like using historical data, you can imagine that you can use all of these like machine learning techniques, like neural network, any type of like ML model to do this, right? But here is also one important constraint, is that you want this model this branch prediction to be fast enough, because you need to execute it in one cycle. You don't want to like have a crazy model. You cannot afford it to have a crazy model. This strategy needs to be very quick. Needs to be executed in one cycle in order to do the task for you. Okay, let me also discuss this example, and then we'll stop, right? And this example is important, but also simple, right? So imagine that you have some benchmark. This spec benchmark is one of those important benchmark out there, but there are other alternative benchmark too. That basically say that, like in the programs, you have 20% load, 10% doing a store, 11% branches, 2% jump, and 52% of R-type, right? And suppose that 40% of the load used by the next instruction, right, and 20% of the branches are mispredicted. Like, again, these are the assumption. This assumption, or the prior, this assumption could change, right? This is one example. It's a type of example that you might see in the exam. And then right, also all jumps flush next instruction. And then the question is that what is the average CPI? And if you remember about performance, we had some elements that determine the execution time, right? We had a number of instruction, right? One component in execution time. We had average CPI, one of the other component, and we had the cycle time. Okay, these are three major components that you remember part of this performance formula that determine the performance of the system, right? So here the question is asking, like, what is the average CPI, right? So one of these components, not asking the execution time, but once you have this average CPI, you can calculate this execution time too, right? And let's quickly go through this, given this assumption that we have. Again, like, this is important, right? This assumption, right? 20% of the branches is mispredicted, and 40% of the load used by the next instruction, right? So for load word, you see that, like, since we know that in 40% of the scenario, basically we need to pay the penalty of doing additional cycle. So in 40%, we basically need to pay this 2 cycle, one additional cycle. By default, if everything is moving in a perfect manner, no penalty, no overhead, whatever, by default, like, and if we have this fully occupied pipeline, then as a result, we get one instruction per cycle. So basically, if you look at the pipeline, one instruction comes out of the pipeline if we have if we have this ideal pipeline, right? But in 40% of the time, in this case, we have this additional thing, right? Due to this assumption, and again, this assumption could change, right? So this is supposed. So this is for the load word, and for BQ instruction, again, like assuming that we need to have this increase in cycle time 25% of the time and 75% one cycle, this would give us 125 CPI for branch, right? So this is the average CPI, 1.4 for load and 1.25 for branches, right? So as a result, if you think about it, so if we add all of this, if we incorporate not only the if we incorporate all of this thing, right? Incorporate all of these type. In this case, like we had this increase 1.4 that we calculated here for load, and also for BQ. For jump, we always basically, again, here we assume that all jump flush the next instruction, meaning that we need to have waste for jump no matter what. So basically, we have this additional all the time. All the time we have this two cycle per jump instruction, right? And the store and R type are not affected really as a result, right? So, but also here you need to also incorporate the prior as well, right? Meaning that in programs that you have in your benchmark, and it is really important, right? What percentage of it is load? What percentage of it is store? What percentage of it is BQ, jump, R type, right? And these are given to you, right? So these are the stats that has been extracted from this particular benchmark. This value could change, right? But these value are coming actually from the actual benchmark, that SPEC benchmark. But again, this value could actually potentially be different in other benchmarks, right? If we incorporate this statistic, so we need to incorporate that only 25% of the instruction are going to be executed in 1.4 cycle, right, on average. Only a small percent, 0.02% of the instruction are jump that are going to pay the price of 2 cycle. Good part of the program, which is R-type, and this makes sense, is not affected on like 1 cycle, right? And 1% doing a store, again, 1 cycle. If you add them up, you get 1.15, which is the average CPI for basically this particular example. So here we calculated the average CPI given, again, like make sure we understand it. Given this assumption could change, like could simply change this assumption. You could simply change this statistic, right? How this CPI value could change? Maybe these statistics, this percentage of instruction could change. These assumptions, 40% of loads used by the next instruction, 25% of branches are mispredicted, or all jumps flush the next instruction. All of these assumptions could change. And as a result, the value of average CPI might change, right? Could simply vary these, and you see that how they affect the CPI, average CPI. I could also come up with some like variances of this type of question, which is easy as long as you build the intuition and you understand this, right? For example, I could ask you, what would be, say, if we come up with a sophisticated prediction, branch prediction, right, that reduce the misprediction to X%, for example. How we could get the best average CPI, assuming that the statistic wouldn't change or would change, or some of these variation, but you get this, right? So this may change into an optimization type of question. This could be could change into a design question, but you can simply answer all of these type of variations, assuming that you build up the intuition how to calculate the average CPI in this case, right? Using this data and the whatever we have discussed in pipelining. And then the pipeline performance can be simply also calculated given this timing paths that we have discussed, right? So for each here, like we formally we have discussed this. We formally doing this basically what is called the maximum time that it takes to do all of these stages. So this is what it determines the slowest operation that that we want to execute, because the cycle time depends on this timing, right? So the slowest stage determine the cycle time, and this also could be incorporated into question and design and really affect the performance, right? So again, one of the other components is the cycle time. In addition to average CPI, cycle time also is important, and one of the components that determine the performance of the system. Typically, we assume that the number of instructions are fixed, right? Especially if we have like hardware variation, the number of instruction doesn't change as a result. If we have like software variation that create these bubbles, no op, the number of instruction may change as a result. But in this case, since we assume that we have hardware resolution, the number of instructions won't change. And once you have this critical path analysis, then you can simply calculate this performance metric, right? this is one example that you know these elements that are constructing your performance model and the delay associated to this. You have seen such example before. Here are pretty much the same, like small variation. You see some of these additional elements that were associated to new hardware elements that we have. Like, for example, you see T equality. This is like associated to the time of this little guy that we add here, right? Because this time, this checking quality requires some time. So we need to add this as a part of the time for decoding, and we have like this additional mux that we added for before this equality. We had mux, one additional mux before in the decoding. Again, you can see all of these hardware elements in each stage, right? How they become part of the critical path analysis. And then we also assume that you see these two here, these are these appeared as a result of assuming that we are writing to the register file or the memory in half of the cycle, and in the next half of the cycle we read from this either memory or register file, and whatever you see in the parentheses are basically the cost for like either of these. So if you multiply it by 2, you get the full latency of each cycle, right? So hopefully this is clear, and you see max here because we want to determine the critical path. So like you remember we discussed all of these paths and we take the maximum one into consideration for calculating the cycle, clock cycle. And here, like, you easily see that this decoding stage might actually, as a result of adding this equality marks here, may become part of the critical path, which is bad actually. This means that this design, this strategy of like adding additional hardware into decoding for simply doing this early branch resolution might not necessarily be the best strategy to reduce the penalty, and we may have a better strategy as a overall. And one reason is that the variation of the microarchitecture may be, the microarchitecture may vary a lot. Some microarchitecture might be a lot deeper. So some of these, I mean, we are now discussing this in the context of MIPS. Some of these strategy, and MIPS are basically the number of stages are like 5, right? And here also we have assumed that, I mean, this particular example, we assume that we have 5 line in our pipeline, right? But if we change all of these assumptions, if we go from MIPS to others where have deeper pipeline, right? Or the width of the pipeline may change, some of these strategy might be really bad. And would show up as a result in the performance analysis. In this case, like in this pipeline version, So the execution time after calculating this, here it turns out to be 63 seconds. If after we incorporated the number of instruction, CPI, and the cycle time, right? And putting into the context of other processors, single cycle, multi-cycle, and pipeline, you see that we get some speed up, right? But this speed up with respect to the cost that we paid is not really massive. I mean, the cost that we paid, we added 5 pipelines, we added a bunch of hardware. Yeah, we got some speed up, like comparing with the baseline that we have, but it's not really that massive. And you see that even like in multi-cycle, if you remember, by making this multi-cycle, we got a larger execution time, basically, or less than 1 speed up, meaning the performance become worse as a result. We discussed this before when we had this multi-cycle. But again, like all of this, again, I want to emphasize, all of this really depends on the assumption that we have. This picture that you see here could vary, this value could vary if we change some of these assumptions. If we change the pipeline depth widths, if we change some of these strategy and so on, the statistic and so on. Okay, let's stop here. We'll meet again on Thursday, and then we are done.
Thank you, Professor.
Thank you. I will stay here for a few minutes. If you have any question, happy to answer. Okay. See you on Thursday. Have a good evening.